Okay, we're back and we're doing some Biot-Savart. This is what I would say many, if not most, students who are new to magnetism find to be the most difficult challenge in your studies of magnetism. Biot-Savart is the general rule that allows us to find magnetic fields due to moving charges. Now, these moving charges could be individual point charges, like a proton or electron, or it could be a bunch of moving charges in something like a current moving through wires. But this is the thing that we'd have to use in general cases, in realistic cases, in order to find magnetic fields produced by the charges. The tricky part of this is just the nature of magnetic fields. When a moving charge creates the magnetism, it circulates around that moving charge or around the current. That's very different from a radial field, something like electric fields shooting out of charges or a Van de Graaff, gravitational fields, radiating towards a mass. Those are all things that we can use something like Gauss's law to figure out. So circulation is different. It's a different geometry. It's a different situation. It's a different type of mathematics. So how do you do it mathematically for a circulating field? For something like Gauss's law doesn't work. Well, the answer is going to be a cross product. Cross products, when you kind of map these out from point to point, can actually create a circulating vector field. Okay, it might sound weird, but with experience, you start to catch on to this more and more, like most things. So here's the expression for the Biot-Savart, or what a lot of people just say is a bunch of BS. The cross product we're talking about is velocity crossed with this radial position vector. So you have some constants out front. Our magnetic constant mu naught divided by 4 pi. It's actually just 10 to the minus 7. And then you have the charge times the velocity crossed with this r hat thing. And that all goes over the distance squared from the charge. So in that respect, for point charges, magnetism still follows the same pattern as gravity and electricity, electric fields. It goes as 1 over r squared for point charges. Okay, so here's the deal. What I want to do is just work through an example here where you have a couple moving charges, one positive, one negative, and we want to try to figure out the strength of the magnetism and the direction of the magnetism over here at the origin. Okay, so we'll try to take about the simplest case we can where things are at right angles to each other. Okay, now the first question you might have is, what exactly is that r hat vector? What does that mean? R hat is first a unit vector, so it has a magnitude of 1. Okay, it won't screw up your calculations at all. And its sole purpose in life is direction. Okay, what direction? Well, for example, in here, this first charge, this negative charge, r hat is a little vector that points down. Okay, now why is that? Well, it's pointing from the charge towards the point that we're trying to figure out the magnetism. That's the origin. So it just shows you what direction you're looking at, trying to figure out the magnetism. Okay, now for the positive charge, think about what direction would r hat be for that one. Well, if we're trying to find the magnetic field at the origin, r hat's going to point from the charge towards the origin, towards the point we're trying to figure out the magnetism. Okay, so in both cases, there's a 90-degree angle between the velocity of the charges and their respective r hats. And again, the magnitude is 1. Now, how do we figure out the strength of the magnetic field? Well, the strength of the magnetic field, okay, the magnitude of this, whenever you have a cross product, if you have constants, let's stick around. And now we're going to have the total charge times whatever your speed is. Okay, that's the magnitude of your velocity. Now we're going to have r hat. The magnitude of r hat is just 1. And then what we need is the sign of the angle between the two. That is, between the velocity vector and the r hat vector. And that's all going to be divided by the distance squared. Okay, now in both cases, sine theta is going to be the sine of 90 degrees. That's going to be 1. Now what about the direction? Okay, well, this cross product that we have, this V cross R hat, in order to figure out the direction, the easiest way is what we call the curly right-hand rule. Okay? Or you can do it what most people do for cross products is they'll use their right hand, so-called right-hand rule. Okay, so for a positive charge, the right hand works. You put your thumb in the direction of the motion. Okay, so if we're looking at this positive charge, you'd actually try to put your thumb, your right thumb, going directly up as you look at the screen. That's the direction of its motion. You want your fingers to point in the direction of R hat. Okay, so for this positive charge, you want to hold your flat right hand, with your thumb going up on the screen, and your fingers pointing to the left. Okay? And the direction of the magnetic field, which is our cross product vector, is your palm. So your palm should be facing towards you, out of the screen as you watch this. That would be the direction of the field over here at the origin. Okay, now the negative charge, you can actually use a left-hand rule the same way. So take your left hand, hold it flat. Okay, send your fingers out and hold it flat. Put your left thumb towards the right in the direction that that negative charge moves, and put your fingers straight down as you look at your monitor, okay, towards the origin. Which way is your palm? Your palm should be towards you again, or out of the screen. So actually, the magnetic field from both of these charges, I'll draw a dot there at the origin. They're both coming out of the screen towards us in the same direction. So that means we can just add these together. Now I'm going to do some symbolically. We want to try to find the total magnetic field. Well, we can use Biot-Savart for each charge individually. We know the direction of each is in the same direction out of the screen. So let's say for that negative charge, we've got our constants. We've got however many coulombs that charge is. Now notice I'm not putting the minus sign in because we already used our left-hand rule to figure out the direction. Okay, we just want numbers now. Whatever the speed is, it's v1 times r hat, which has a magnitude of 1, and then the sine of 90 degrees between your motion and that radial vector. And that's all going to be over r1 squared. That's the distance from the charge to the origin. Now we can just add to that because this vector is in the same direction. We can just add them together. We've got that positive charge times whatever its speed is, v2. Its r hat also has a magnitude of 1, the sine of 90 degrees. And that's all going to be over r2 squared. So if we actually had numbers for this would work out beautifully. We can just add these numbers together. Okay, sine of 90 in both cases is 1. And so basically what we'd have is we'd have this magnetic constant divided by 4 pi. We'd have the charge times speed 1 over r1 squared plus the positive charge times v2 over r2 squared. And that would be the total magnetic field strength. And it's becoming out of the screen as the direction. Okay, so for point charges, this tends to not be so bad. I did want to show real quickly this picture here. If we had a positive charge moving to the right, I put 2 points there, P1 and P2. And how would you handle these? Okay, for example, at P1, what would your r hat be if we're trying to find the magnetism up there? Well, the r hat is going to be pointing from the charge towards P1 at that angle. So now you no longer have a 90-degree angle. What does Biot-Savart say about that? Okay, so for P1, the magnetic field strength would be our constants, the charge times whatever the speed is. R hat has a magnitude of 1, but now we really would have to use sine of that angle. And it's something less than 90, so it's going to be a little bit weaker than it was as if it was at a 90-degree angle. And then over whatever that distance is squared. Now, check out another special case. What about at P2? What if you're in front of a moving charge? And you ask the question, well, how much magnetism is going to be out at P2? Watch what happens if you're in front or in back of a charge, for that matter. Biot-Savart says we have our constants, the charge, the speed. R hat is 1. Now, think about the R hat for P2. R hat is now parallel to your velocity if you're out in front of the charge. There's a 0-degree angle between that direction vector and your motion. Well, sine of 0 is 0. So there is no magnetic field in that line out in front of a moving charge, or for that matter, at any point directly behind the moving charge. There your R hat points backwards, and you'd have the sine of 180 degrees. So there'd be no magnetic field. You only have magnetic field off of that line of motion. And it's a maximum, you get the maximum strength, the most bang for your buck, if you're at 90 degrees relative to the particle and its motion. Okay, so all of that is kind of wrapped up in this funny looking expression here for the Biot-Savart rule. And this is what we need to use to get the exact answers, the actual magnetic field at any location around a moving charge. Okay, so I know it looks weird with the cross product, but I hope this helps a little bit, getting some examples under your belt. And until next time, we'll see you later.